You can start, Ray.
Well, thank you, everybody. Thanks, everybody, for your patience. My name is Ray Hill. I'm the person on the screen you see is my incredibly helpful baseline guy for the Zoom and Professor Dr. Clemens Schwarzinger, who's been very, very helpful and supportive of Gemquest for the last year. And we really appreciate his time and contributions to help the program go. Gemquest is a program that's been going now in its fifth year, once a month on the last Sunday of the month. We're nonprofit, nonpartisan, and we try and keep ourselves above the fray, if you will, so that we're not giving anybody any free advertising, particularly. We're just trying to give everybody an opportunity to get GEM education at the highest level. So today, unfortunately, as you've probably been witnessing, for some unknown reason, Justin, our proposed speaker, has not remembered to contact us, and so we're going to move forward with a completely different program, and it might actually be more scientific and equally of interest. Uh, the person who's going to step in, Scott Sucher, is a very talented young man who's a cutter, and he is going to be doing along, on the September program. He's going to be showing us, sharing with us a rather exciting expedition that he and Peter Young did to various gem mining locations in Africa, in Kenya and um, oh dear,
Tanzania.
Tanzania. Tanzania. And so we're looking forward to seeing a little bit about the geology and the exciting peoples that are the miners and so on next month. So I'm very much looking forward to seeing what he and Vitor put together. Um, so today we're going to get a review of the synthetic diamond industry, and if you could take it away, Scott. Thank you very much for stepping into the fray. 2 months in a row, my goodness.
All right. Let me get my presentation set up.
And if you could turn your volume up just a little.
Oh boy, you're asking for a lot.
Oh, sorry.
Okay. I think my video or my audio is up as high as I can get it. I'll put my mouth closer to the microphone. All right, can you see my screen?
Yes.
All right. We'll just launch right into it without any other indicators here. Okay, what I'm going to talk about here is just understanding lab-grown diamond. And this is basically where the stuff comes from, how it's created, how it's colorized. It doesn't have a whole lot as far as market forces, because as we all know, that's generally when it comes to pricing lab grown, it's in a downward spiral. And we have as yet to reach the bottom. If anybody needs to contact me, this is my contact information. Confirm you are not getting any other of the extraneous stuff I'm seeing on my screen. Are you just seeing the slide?
Yep.
Okay, excellent. All right. Now don't worry about that. Just real quick, I'm known for creating replicas of famous diamonds for the last 40 some odd years. Did some work with the Discovery Channel and the Hope Diamond. And this is what a guy looks like when he's handling the unset Hope Diamond. Then I did some work with the Natural History Museum in London on the Kohinoor, resulting in this article in Gems and Gemology. And then Natural History Museum in Paris contacted me to do some work with the French blue diamond. And that ended up with this article in Gems and Gemology. I also did a separate article on the Tavernier blue diamond, which is the grandparent stone of the Hope diamond, with yet another article in Gems and Gemology. And then National Geographic heard about this for somehow, I have no idea. And that resulted in a National Geographic special. And then 2011, I was the keynote speaker at GIA's Diamond Symposium. I haven't just been sitting back, but since then I've done work with GIA, JTV, Yale. Tiffany contacts me from time to time, numerous reference books, et cetera, et cetera. All right. All right, your current sources right now, you have your natural diamonds. and you have your lab-grown diamonds. And your lab-grown diamonds, you have two types. You have chemical vapor deposition, and these always end up as cubes or rectangles. And then you have your high pressure, high temperature. And I know I'm going to screw this up. I know there's crystallographers out there, but these all grow in like a hexoctahedral dodeca something form that basically a lot of sides, and it grows in these interesting shapes. So your natural diamonds are formed anywhere from 150 to 450 kilometers deep. By the way, there are deep mantle diamonds now that apparently go much deeper, and those are your pinks and reds. But down at those depths, you have a temperature of about 1100 centigrade and about 735,000 psi. So diamond is kind of an interesting thing in its formation in the natural world. And most of your diamonds are actually 2 billion years old, and they're carried to the surface in these kimberlite eruptions. And up until the 70s, we thought kimberlite was the only material they were found in, but in fact, they're also found in another material called lamproite. And during the eruption, it takes this eruption about 1 hour to reach the surface. So you can imagine the energies involved to punch through hundreds of miles of rock in 1 hour and to get to the surface. Okay, and the lamprite's been around since 1979. And just in case any of you are interested, the lamproite can be as new as 55,000 years old, but the deposit in Arkansas is a lamproite deposit. Only about 1% of any deposit yields diamonds, period, let alone economically. And on the average, you get about 1 carat of diamond per every ton of ore. So just in like hard rock mining, the secret here is that the more rock you move, the more good stuff you find. Right, so the lab grown, I've already mentioned the CVD and the HPHT types, and we're going to look at those individually. And one is not necessarily better than the other. I've seen all kinds of stuff online where one reference says, oh, CVD is better because of this reason. And HPHT says, oh, this is better than CVD because of this reason. I'm not a diamond guy. I just like creating replicas. And as a result, I don't get into one better than the other. As long as I can get what I need, I'm a happy camper. So I'm a little parochial in that respect. Okay, as far as diamond crystals, your natural diamonds are frequently found as octahedrons. This was the predominant diamond shape of the early diamonds coming out of India. They would find these perfect little octahedrals in the alluvial deposits. Now the CVD, it grows vertically in the squares, as you can see here. So basically it grows from the bottom up, like in that middle video or picture. HPHT, here you go, the cube octahedron, and it grows on pretty much all the sides. Now, as far as CVD, excuse me. As far as CVD, they're grown under vacuum at 1100 degrees Fahrenheit. Hang on a sec while I try to get rid of some extraneous stuff on my screen. All right, and what they'll do is they'll put up to 30 seeds in a single chamber. And under chemical vapor deposition, you could deposit about 100 microns in depth per hour. Obviously, the faster growing rate, you get more inclusions, but they can go as slow as 0.1 microns per hour. So this can take some time for these diamonds to grow. And I found this interesting from a chemical aspect in that the reactant gases is 99% methane with 1% hydrogen. And they need the 1% hydrogen to convert to ensure that the diamond vapor doesn't get deposited as graphite instead of diamond. So they heat up this gas mixture. You can see this plasma here, and they heat over the seed, and they heat it using either filament or microwaves, and it just slowly deposits on the surface of the crystal, and it deposits there because it's a little bit cooler than the surrounding environment. So if you're using a hot filament, you're looking at 10 to 100 microns per hour, but it's less pure. Using the microwave, it's slower, but you can get flawless material. And the carbon is deposited on the cooler surface. And after 3 days growth, this is what you look at when you pull it out of the reaction chamber. So the picture on the right is 3 days worth of growing. You can see in the picture on the left, the graphitization of some of the
It's not
diamond.
showing,
That,
not showing.
say again?
It's not showing what you're talking about. It's still showing the machine.
Yeah, interesting. Okay, let me check what's going on here. Let me back up to the machine. All right, can you see it now?
Maybe you have to click into the presentation when you did something else on the screen.
Oh, perhaps. There you go. Okay. All right. Do you see an orange wafer glowing?
No, we still see the CVD chamber.
Okay. I'm hitting the share button. Let me change the window. All right. Do you see the Zoom window?
We still have the one slide.
Oh boy.
Maybe close and restart again.
All right. We'll give it a shot. All right. I'll do that. It's asking me if okay, Clemens, should I just go ahead and leave meeting and start all over
You
in the
can, but
process?
I think it's not necessary. You just have to close the PowerPoint presentation.
All right. Oh boy, I'm not that familiar with Zoom. I don't really want to cancel, so let me see what's happening here. If you see anything change at your end, okay, I'm going to hit stop
Okay.
share.
Now you stop sharing.
And now we're going to the PowerPoint slide and share. And do you see?
Now we see this wonderful orange.
Ah, excellent. Okay. So
Thank
here you see the seed crystal, and the plasma of carbon atoms is hovering right above it. All right, so if you're using the hot filament, your carbon gets dissociated from your methane, and you can deposit up to 100 microns per hour, but it's less pure. Using the microwave, up to 10 microns per hour, but that results in a flawless crystal. And your carbon is deposited on the cooler seed surface, and this is what you look at after 3 days of growth. So on the left-hand picture, you see the graphitization of the carbon. But where the crystals are, you get your diamond deposited. And on the right-hand picture, you have your crystal of CVD grown diamond. Now we take a look at the high temperature, high pressure. What happens? You have your seed diamond in a chamber that's filled with a metal catalyst, usually nickel, iron, possibly cobalt. And now you're just going to squeeze the living stuffing out of everything as you heat it up. And your carbon source in your seed could be anything containing carbon. And this is where, if you want to take your cremated remains of dear Aunt Agnes and turn it into a diamond, this is how that diamond would be created. But anything that contains carbon is fair game. And it's heated in what's known as an anvil. You see your picture at the bottom, and you can see 6 cylinders. And basically, you are just squeezing this to about 800,000 psi and 1200 degrees centigrade, and it converts the carbon in whatever material it's in into diamond. So the metals will melt and dissolve the carbon. And you can see in this picture that it is cooler at the base. So your carbon atoms migrate around until they find that cooler seed and they start growing. And then you wait about a month. Now we've all heard that these things are grown in factories. You can see the size, well, the quantity of machines in one of these factories, but you can see the size in the right-hand picture. These chambers are far longer or larger than anything I would have ever expected. And so about 1 month later, you just remove the diamond crystals and you cut them. And this is what they look like coming out of the chambers. Now, there are several diamond types, and I'm only going to talk about the predominant four. And it doesn't matter if we're talking whether it's natural diamond or lab grown in either of its forms. But your type 1 diamonds, this is 95% of all your natural diamonds, and they have a nitrogen impurity. And that nitrogen impurity usually gives them some shade of yellow. Now, a type 1A, your nitrogen atoms are in pairs, and this gives you your pale yellow and your brown diamonds. If you have a type 1B, you still have nitrogen, but you can see that they're randomly scattered throughout the crystal, and this results in your canary diamonds. The third type are your type 2 diamonds. These have absolutely no nitrogen whatsoever. These are generally formed naturally under high pressure over a long time. Your type 2A, these are your absolutely colorless diamonds. But if you throw in a little bit of boron and scatter it throughout the crystal, it'll make them blue. So these are the four types we're talking about. And I'm sure a fair number of you out there already have, GIA certifications as GGs. And I'm not sure what MA gives. And you could probably talk about this more into greater detail as far as the different subgroups. But for today's purpose, we're just going to talk about these four real briefly. When it comes to colorizing lab-grown diamonds, the eventual color that you want depends on the material that you're starting with. Now, if you want to create a green lab-grown diamond, you absolutely must start with a type 2A. So no impurities whatsoever, absolutely clean as far as that goes, nothing but pure carbon. And you can see here in the table that it's broken down as far as your natural diamonds, your anything but 1A, those are fairly rare. Like I say, the 1As, they make up 95% of all your mined diamonds. HPHT and your CVDs, you can create, actually you can create all four of them depending on what you desire. Now, when it comes to colorizing your lab-grown diamond, you can use radiation. This actually disrupts the crystal lattice, just like it would, say, in the Dresden green diamond for natural diamonds. And what happens is that your carbon atoms shift their position in the crystal a little bit, and it changes their light absorption properties. And in the case of the Dresden green, the resultant color is obviously green. When you're talking lab-grown diamond, they use neutrons. And you can see here it penetrates through the entire stone, making your colors anywhere from green to black. And then you can throw in an additional heat treatment up to about 900 degrees centigrade to produce some different colors. This is still a little bit in its infancy as far as colorizing lab-grown diamonds. I'll talk about that a little bit more. And you can also use electrons, and you can see here that your blues and greens, but it only penetrates about 1 millimeter deep. But again, even with the electron treatment, they can produce orange, yellow, brown, or the pink colors. Now, in my particular case, this is extremely important. Anybody who knows me well knows that I create lab-grown diamonds out of cubic zirconia. Or excuse me, I create famous diamond replicas out of cubic zirconia. I have recently partnered with a diamond growing company in India, And we have actually created half-size replicas of the Dresden green diamond and the Wittelsbach diamond out of lab-grown diamond. We did them half-size just because it minimizes the technological risks and costs, but colorizing them is still in its infancy. We can't quite dial in the precise colors we want just yet. It's a little bit hit or miss. The Dresden green, as far as I'm concerned, is spot on. The Wittelsbach is a little bit too pale, but it's still a magnificent replica. The eventual goal, once technology catches up, is to recreate some of the world's famous lost diamonds out of lab-grown diamond. When I say lost diamonds, like the original Kohinoor at 189 carats, the Florentine, the Nasek, I can name a bunch of them, but that's the eventual goal. All right, so you can also do the high pressure, high temperature treatment, and either type of your lab grown diamond can be colorized. So here you see a before and after of the result. That before picture, a bit on the brownish side, I'm not sure what color you want to call it, maybe a mauve, and you can see what happens after you do a subsequent colorizing treatment. And what's happening in this particular one, you're turning the diamond from a 1A into a 1B. So you're basically splitting apart those nitrogen pairs into single isolated nitrogen atoms. So here's the before and after, basically your 1A into your 1B, and you can see, or the 2B, excuse me, the 1B, but you can see how the 1B, the nitrogens have migrated around individually. Now your high pressure, high temperature created diamonds, a lot of times they end up with color zoning. And here you have a specific blue diamond, and you can see where one part of it's a type 2A, part of it's type 2B, part of it's 1B. With CVD, you have a little more control over the process, so you don't end up with the zoning. And you can imagine the difficulty with the HPHT trying to get a consistent color throughout the entire stone, because you're starting with basically an impure carbon form and hoping everything migrates in the right direction. And it may or may not pick up impurities along the way that will affect its eventual color. Now with CVD, yes?
Yeah.
Okay. With CVD, you don't have that issue because you just basically start with pure methane with that little bit of hydrogen. So the introduction of impurities really doesn't occur unless it's intentional. All right, so here's a yellow diamond that they treated. It was originally olive brown, and it had the peak at 926 nanometers before treatment. They heated it up to 2000 degrees centigrade at 65 kilobars of pressure for 10 minutes. And I'm not sure what happened to my picture. All right, well, you'll just have to take my word for it. I think this is actually the one that I showed you a few slides ago. All right, now colorizing lab-grown diamond, I found this wonderful little chart. And basically, depending on what you start with, it shows you what you can end up with. So let's start at the bottom. You have your colorless or a blue diamond. So you're looking at either your type 2A or 2B. And you can start your different colorizing processes. So if you start with your type 2A on the left, where you have very little impurities, you can start heating them and treating them under different temperature and pressure schemes. Actually, in all of these, you can do this. And like on the right-hand side, you can start with, if there's nitrogen in there, you can irradiate it and you can get your blues and shades of green. Then you can anneal it under further high pressure, high temperature. You can get your pinks and reds, and your browns is kind of a mixture of everything. So this just shows you that you can start with any one of these types and then subsequently treat it, hopefully to get the color you want. In my particular case, we try to match colors as much to the natural diamond as possible. And again, we're still exploring the fringes of that envelope because nobody's really tried to dial in specific colors on a consistent basis to match something that was already pre-existing. So here's a comparison between the two. I'm not going to read it. I'll just give you guys about 10 seconds to read it on your own. The one interesting thing I find is the last line, CVD, it's basically a desktop machine. For HPHT, they weigh up to 70 tons. Try convincing your wife to put one of those in your living room. As far as commonalities, they both can fluoresce and they both occasionally phosphoresce. And that's still under some study. Now, to give you an idea, this is the world's largest lab-grown diamond. It finished out at 75 carats. It started as a 190 carat piece of rough, took roughly 9 months to grow and 30 days to cut. This is not an easy process. To give you an idea of what my future goal is in my little project, the historic Kohinoor weighed 189 carats. That's going to require a piece of rough probably in the vicinity of 600 carats. We don't know how long it's going to take. There hasn't been a reaction chamber built big enough. So we have to overcome all these technical hurdles. But just like anything else, if you can show folks that there's an economic requirement for the equipment, hopefully they'll start producing it and we can start recreating some of these famous diamonds. Now, the largest HPHT grown was a 56 carat piece of rough. It took 18 days to grow, and it's this 20 carat yellow diamond. All right, now here is my Wittelsbach replica. Again, this is half size. When I say half size, I'm talking dimensionally, not by weight. Off the top of my head, I believe the Wittelsbach is probably about 24 millimeters long, so this is 12 millimeters long. Interestingly enough, because of the mathematical property of squares and cubes, even though it's half the dimension, it's 1/8 the weight. So this weighs a little bit less than 5 carats, but it is a 5 carat lab grown blue. All right, so quickly in summary, you have 3 sources of diamonds. You have your naturals, and then you can either create it using CVD or HPHT. The growth processes are radically different. You do have your 4 types, and depending on what you start with, depends on the colors that you can end up with via either radiation, high pressure, high temperature, combination. And again, we're still exploring all of those little issues. And then what you start with here in this chart can helps explains what you can end up with. And then we have our chart of differences. I've kind of wondered, now I have not approached this with my wife, and she's sitting next to me with earphones on, so she doesn't have to listen to me. But I was wondering if she would let me buy a CVD unit so I can start playing around on my own, maybe put it in the garage or on her side of the bed. And the technology is always improving, so you never know what's going to come down the pike. I'm a firm believer in my lab-grown diamond project in the motto of the British SAS, their Special Air Service. And these are basically your long-range desert patrols from World War II. And their motto is, who dares wins. So you have to be able to be willing to accept the failures, and I failed 90% of the time, to get to the successes, especially when you're pressing the limits at every single step. So there you have it in a nutshell. I was able to fill in a little bit. Does anybody have any questions?
Well, first of all, I want to thank you, Scott, for stepping into the fray. That was wonderful. I have a question of sorts. I've been advising people who want synthetic diamonds that they are going to be dropping in value as the process becomes more efficient. But I do believe, and I'd like you to correct me from what you know, or anybody else actually, but I do believe, and I advise them that the perfect D flawless synthetic stone is still very rare in comparison to what's out there. And so if you want to invest in a synthetic diamond, go for the highest possible qualities of clarity and color that you can get. Because it's, as far as I can see at this point anyway, it's going to be a long time coming before that's a common occurrence.
Yeah, again, the technology is always improving, and that is the goal, is getting your D flawless. The trick in our particular case is getting that D flawless in the sizes that are going to be required. And as far as pricing, yeah, prices are still coming down, but there must be a basement somewhere, because I seriously doubt that a 70-ton HPHT machine is going to cost much less, especially with tariffs coming online. God knows what the economic industry, the economies are going to affect industries across the planet, and especially this one. So, what's really going to happen is anybody's guess. Any other questions?
Clemens, do we have any questions on chat? It looks kind of bare right now. Yeah.
No, we
No,
don't
no.
have any questions in the chat.
Wow, I must have been pretty good
Diamonds.
then. All righty, well then that's all I have. If you don't have anything else, we'll put Clemens
Well,
on base.
there's a question from Robin at the British Museum. Could you actually say it verbally for us, Robin, please?
Yeah,
Can you
sure. Can you
unmute?
hear me
Unmute?
okay? Can you hear me okay?
Yes.
Yes. I was wondering with the HPHT diamonds, how many diamonds grow at a time in the machine? Like, is it just one that comes out, or do you get multiple crystals?
My understanding is that you can get multiple crystals over time, and I believe they can go as high as 30 that can be produced. But again, it depends on the size of the reaction chamber. How big a piece can you crush?
Yeah,
Thank you.
I know pretty much the same. It depends if you have a seed crystal. If you have a seed crystal, then you have preferred crystallization on the seed crystal. So you try to get one large crystal. If you have spontaneous crystallization, for example, if you go for grinding diamonds, then you have a couple hundred, but just grain sizes of 800 grit, 1000 grit, something like this.
Yeah, I guess it all depends on what your target is,
Exactly.
depending on the market niche that you're trying to fill.
Yeah, I found from the dealers that the smalls between 1 and 5 points are almost as inexpensive as cubic. So they're putting them out at a much faster pace and much less cost.
Yeah, I have heard from a reputable source that to create a diamond of about a piece of rough that'll cut a diamond of about 1 carat. So you're looking at maybe a 3 carat piece of rough, costs about $20 to create.
Wow. I remember when the first one was created in New York State, and the amount of electricity and power that was used to create that diamond under pressure was close to $1 million for that first 1 carat diamond. So this has come a long way from them.
Yeah, and it'll be interesting to see how this develops from both the economic aspect and its impact on the jewelry industry, but also from the scientific aspect, because most of us probably know that diamonds have some rather unusual properties. I mean, it has the highest thermal conductivity. It's transparent to infrared radiation. That's why the Venera probe had a 25 carat natural diamond as a window, because could withstand the atmosphere on Venus and the pressures, and they could get valid information, obviously, before it crashed. So it's a fantastic material. It's great for heat sinks. You're going to start finding them in computers to get rid of the excess heat. Uh, so who knows where it's going to end up? I find it fascinating because I'm a techno geek and I have a chemistry degree and another degree in semiconductor manufacturing. And when it comes to lab grown diamond, both of those degrees overlap. So it allows me to understand these processes in great detail. And I just wish I had more time to actually study it so I could dive into it deeper.
That actually brings up an interesting non-gemological topic, just as an aside, is that they're now doing vapor deposition on other media, like to act as a heat sink, so with a very thin layer of diamond heat vapor deposited on the surface. And I think that's going to be an interesting new direction for electronics, as they're going to start seeing that kind of thing happening.
Most definitely. And you can imagine in the world of abrasives, it's not just diamond grit. Now you can deposit the diamond, say, directly on some kind of a bit that you're going to use for grinding. Just make it in whatever shape you want, deposit the diamond on it, and then just go and do your thing.
Yeah, and of course, these diamond crystals are all consistent, unlike the Bort or the industrial diamonds that are used in the past. So they have some different kinds of integrity than the old diamond grit used to have.
Yeah, and you can see the consistency in the CVD diamonds in the picture here in the upper right, where they're coming out just, you're basically mass producing these suckers, and every one is just like its neighbors.
We
Yeah.
have two new questions here on this site. The first one is the seed crystal visible within the lab-grown diamonds?
No, it is not.
No, it's usually cut away. And the second one is a little bit longer. I recently saw a parcel of strong brown and yellow diamonds, which had very strong yellow, green, red, and other color fluorescence. The dealer was selling them as natural untreated, but when tested, I found they were irradiated. However, I'm wondering if they were in fact synthetic diamonds. Is there any way of knowing they had the color zoning you described?
Ooh, that is, I'll tell you what, I'm going to weenie out on this one. I'm going to leave it to the gemologist to determine that. Um, from my non-gemological training, but highly scientific and chemical training, personally, I don't care what the dealer says. I want to see a lab report from a reputable lab. There are lab-grown diamonds, like in any, I'll say, counterfeit item. It's getting so good that you can make them look like anything. It can be real these days. And they're getting better and better at making counterfeits across the board. So to say that, if that's a red diamond, I'm going to seriously doubt that red diamond is a natural red. It's probably lab grown. It's definitely irradiated unless you get a lab report. So just like anything else, caveat emptor, let the buyer beware. So anybody can say anything. In God we trust, all others pay cash.
So maybe I can tell a little bit about my experience here from the lab, not being a gemologist, but doing some diamond testing from time to time. I have not yet found synthetic diamonds which I could not identify as synthetic diamonds. So identifying synthetic versus natural is rather, I would say, easy in most of the cases, if you have the right equipment, of course. When it comes to color, source of color, then it's getting really, really hard to tell. I mean, a couple of colors are obvious. You see some irradiation defects, and then you can tell, so this blue is not natural. Very often, just looking at the diamond is enough, because if it's just an unnatural color, then it's what it is. It's not natural. But if you look at greens, for example, so Scott already told us the source for green in diamonds is irradiation. And this is just very tiny point defects that are on the surface. And you can reproduce them with a neutron beam, with a alpha irradiating material, for example. So the difference between the natural and the synthetic is very, very narrow. It's just the intensity of the radiation and the time. And detecting those for many labs might be a problem, but there are labs out there. I just want to mention one name here, Thomas Heinschwang. He has spent years and decades on especially green and yellow diamonds, so he can tell the difference. And also some of the bigger labs can tell you definitely also the source of color, if it's natural or not natural. But synthetic, not synthetic, there are a couple of easy tests. For example, if your fluorescence is red, it's it is definitely not a natural diamond. For the others, you have to be careful. And very often what helps you at the end is observing the fluorescence pattern like that you see in the HPHT treatment, that you have cubic and octahedral structures that have different fluorescence. And if you have a deep UV irradiation under your microscope, then you can tell them apart with lots of experience, of course.
And of course,
And
I
you had
think
to
the
make
key
me
word, go ahead.
you had to make me smile when you said it's relatively easy. Says the guy with the PhD to the Schlepp stone cutter of the mountains in New Mexico. So it depends on your perspective. Just
Exactly.
remember, it's one thing to be ankle deep in horse manure and another to be upside down at the time.
Yeah, that's absolutely right. But it's always going to be, if you have a stone like this, if you try to invest a couple, let's say $10,000, $100,000, you should be able to go to a reputed lab or to go to some specialist to ask them the right questions. What is important is for you to see, what can I do as a layman, for example, and where are my limits?
I mean, I think it's the old adage, if it looks too good to be true, go to a gem lab. But
If it
when it
sounds
first
like a
came
duck,
out,
it walks like a duck, then it's a duck.
when diamond imitants started proliferating, and I'm old enough to remember that, cubic zirconias first came out, and Burke's, which is one of the biggest jewelry stores in Canada, chains at the time, they had people coming in. Oh, my aunt died. I want to get rid of this jewelry, and they had a cubic zirconia cut in an old-fashioned cut and reset into an old-fashioned ring, looking like it was a flawless, 3 or 4 carat diamond. And of course, the jeweler was saying, "Oh my goodness, this is such a deal! And what do you want for this?" He said, "Well, I just want to go in a hurry." And a lot of jewelers were duped by people who are taking advantage of the new imitants and simulants. But now I think this job becomes much more difficult because we're dealing with diamonds that are diamonds, and even though they're synthetically made. So I'm expecting that out there are people that are cutting the synthetics in the old-fashioned designs and put them in old-fashioned rings to try and hawk them as if they were natural. And I think this is going to hurt. Ultimately, it's going to hurt the value of natural diamonds as it goes by, because it always will make people wonder: is this real or is it synthetic? And we're going to have to pay those lab fees to find out. So yeah. So this is a very topical topic, and I thank you very much for stepping into the fray, Scott. It was much appreciated. But I heard a little mouse say that they might also talk about chemistry and gems afterwards. Is that still true? Is that still possible, Clemens?
Yeah, sure.
Um,
Okay. So wow, we had a double whammy last time, and now we're going to get another one this time unexpectedly and for free. This is amazing. So Dr. Clemens Schwarzinger, please step into the fray and let's hear what you have to say about this.
Okay, before I give you some insight into the chemistry, I'd like to draw your attention to those who still have free time in September. So in about 3 weeks from now, we have the FEEG symposium here in the town where I was born, in Linz, Austria, with a wonderful program, a couple of speakers that you might be familiar. So those who do not have yet travel plans, take your chance and visit us in Linz to see the award ceremony, or for all those guys who finished the FEEG program, this Fédération European Gemology. I'm not good at French, so it's a European gemology program, and this is the award ceremony. So, but now let's go into something a little different, if I find it. So, okay. Okay, here we go. A little bit on color and chemistry. And yeah, for the chemist, Scott, it's nothing new here. We have the periodic table of elements. This is something that chemists live on. Usually, organic chemists, we just need 3 or 4 elements. Everything else is for these mineral guys and inorganic chemists. But today, it will be of interest. So I just have no idea. Okay, so have you ever wondered, first of all, what people like me are doing in the lab? Or why would we need the chemical composition of a mineral? I mean, obviously, we know that the chemical composition identifies a mineral. In the easy case, we have, for example, a corundum, we have aluminum and oxygen, and they form aluminum oxide. So I'm not talking about this main composition of chemistry today, but a little bit on the tiny elements that are just sitting in the place somewhere in the lattice of these, and that may give you color or any other defects. And how do I try to analyze those with a machine that's called laser ablation ICP-MS? ICP stands for inductively coupled plasma. We can have this plasma like we have in the CVD synthesis of the diamonds. It's here in this chamber, and it's like a little sun. It has temperatures up to 10,000 Kelvin, so extremely hot. And if you put anything into such a plasma, it will decompose. It will decompose into atoms and ions. And the ions is what we are using, because here in this left part of the machine, we separate the ions and identify them. What we have on the right side, coupled in our case, is a laser ablation. That means we put our gemstones in a small chamber and we shoot at it with a laser. I think there's a nice slide here. There's a demantoid garnet, and you see here on the girdle 3 small circles. We use something like a diameter of 50 microns, and we shoot real holes into our gemstones. But the holes are very tiny, they're shallow, like 1 to 2 microns in thickness, and you wouldn't see them if you're not looking at them with a microscope or a loupe. And if they disturb you, you just repolish them without any loss of weight, typically in the thousands, 0.001 carats range. So with these 3 small holes, we get 3 times the complete chemical analysis of our gemstones. So here's a little bit more traditional plot of what we have. We have the laser swords from Star Wars, of course, and we shoot at the surface of our gemstones. You see here, if you look careful, there are 2 lines of small points running from bottom left to top right. And these are all the points where we have shot with the laser onto the gemstone and then sent them with a gas stream into the plasma where we ionize them. And then we have a mass spectrometer. The mass spectrometer is the analytical tool of choice for any chemist because it can tell you almost everything at a very high resolution and a very high separation efficiency. So what it does now, it separates our elements by their weight, like calcium, iron, manganese, and magnesium. And then we have a detector, and the detector detects how much of each of these elements is present. And then at the end, we end up with a table. I just plotted here 4 elements. Currently, we're running about 35 to 40 elements in a single run in 30 seconds. We have all these elements just to make trace element analysis and to collect data in the first place. So looking again back to our periodic table, we do have some limitations. All the elements that you see here in white, those are the ones we cannot measure. I mean, these are the noble gases. We don't need them. Hydrogen, very rarely. Carbon, in some cases, yes. But if it's a carbonate, you have other techniques. Nitrogen, oxygen. The only thing that I'm really missing is the fluorine, because fluorine in apatite and topaz would be very, very effective. All the others we can measure, except the ones down here. They don't have any stable isotopes. So these are the radioactive elements, synthetic elements, which anyways are not of interest. Mostly of interest are the things here in this top range, the yellow ones and the blue ones. What does the color indicate? The color indicates how precise we can measure them. Like the blue ones, you see it here below 0.1 to 1 ppt. Now, what does ppt stand for? Parts per trillion. You see parts per million is 1 in a million. Parts per billion, this is like sulfur here, or the red ones, we can measure them down to 1 part per billion, and then we go down to 1 per trillion, 1 part per trillion. So this is a very, very sensitive machine, which is necessary because sometimes we need to differentiate between 1 ppm there or not there. So what do? We have samples like here a bicolor tanzanite, we have the bluish purplish rim here at the side, and then in the base we have a brownish material, and we just ran from the left to the right a couple of spectra, and you can see them here. Vanadium, for example, vanadium is extremely high in the outer side where we have the blue color, and then goes down where we have the yellowish brown. On the other side, you have gallium, for example, increasing towards the center, and especially titanium, you see an increase. So the yellow is somehow correlated to the titanium, whereas the blue is known to be due to the vanadium. So this is the simple things that you can make. In terms of gemology, one of the first things that laser ablation has become very famous was the detection of beryllium diffused corundum. So in corundum, very frequently you have some issues like it's not clear enough, there is rutile silk and so on. So people have early on figured out that if you heat treat them to very high temperatures like 1800, 2000 degrees centigrade, you can remove lots of these inclusions and you can make a little improvement in color. And just at some point, people were heating other materials as well, one of them being chrysoberyl. And chrysoberyl includes the element beryllium. And they had some remnants of this chrysoberyl still left in their furnace, heated the next batch of sapphires, and then they found out they turned a wonderful orange. So what happens is that the beryllium, which is a very small element, is small enough to diffuse into the crystal, into the cut gem, and goes down a millimeter, maybe 1.5 millimeter. And then it produces, due to a complex mechanism, this orange color. And this is extremely hard to detect because usually people, when they were looking at chemical data, they were using microprobe or X-ray techniques, and they're blind for beryllium because beryllium is just too small, so they don't see it. It was just possible by, for example, slicing a corundum crystal and seeing that in the core you have a different color than in the rim, then it's obviously a diffusion from the outside towards the inside. And with laser ablation ICP-MS, you can see that you have a concentration at the rim of 8 ppm, which is enough. Going down to 5 ppm, in the core you have nothing, and back here at the tip, we get up to 8 ppm. And I can tell you this is a rather high concentration of beryllium. Even just 1 or 2 ppm of beryllium would be enough to give the gem a nice orange color. And now this is one of the methods where, one of the cases where laser ablation ICP-MS has become famous for, to be able to detect this beryllium treatment in the corundum. I just got a sample last year from, I think, Madagascar, from Carmina Locker. And it's a wonderful sapphire, bicolored. It has a red core and bluish purplish outside. Again, we measured lots of points from the left to the right. And you can see here, I took out just 2 elements. So you have titanium, high concentration at the rim, nothing at the center, high concentration at the rim, and chromium just the other way around. So the red, as we know in corundum, is due to chromium, whereas the bluish color comes from the iron and titanium. Iron very often is just the same concentration. It just takes a couple of ppm, like in this case 400 ppm of titanium, that give us this intervalent charge transfer complex. I know lots of complicated words that we have here, but just for the information, you need titanium, you need chromium to make these bicolor sapphires. And they grow from the from the center towards the rim just by having different solutions where they grow in with different chemical compositions. Yeah, and another thing that people always associate with laser ablation ICP-MS is the detection of Paraiba tourmalines. So we can have lots of discussion about the term Paraiba tourmalines. Paraiba, for those of you who do not know, is a state in Brazil. And in this state, there was a mine in the about 1980s, the Batalha mine, where bluish, Windex blue and other colored tourmalines were found for the first time. So they were so special that at some point they got the name Paraiba tourmaline. And then they were found in the neighboring state of Rio Grande del Norte. So even in Brazil, not everything is from Paraiba. And even later on, I think Nigeria, Mozambique, that's pretty much the sources where you can find tourmaline with the same chemical composition. And this is now what we define the Paraiba tourmaline or Paraiba type tourmalines, that they are copper bearing. So you have copper as well as manganese, and by just running here these laser ablation ICP spectra across this crystal, you see that you have different elements, and you can see how much of the elements is there. I just skip this one and go to the next slide. So this is more what people associate with this Paraiba color, this bluish color. And you see that here in the core, you have manganese and copper. Copper make it this bright Windex blue. Manganese is a pink chromophore. And so you see here this stripe of perfect blue color. This is where you have the maximum concentration of copper. You have more copper than manganese. And again, then manganese and copper in various concentration, giving you all these different colors. What does it help us? This is the good question. Now, we did the same in my lab with demantoid garnet, for example. So demant garnet from Russia can be green in its natural state, but it can also have some yellowish and brownish colors. And if you heat treat them, then they turn to green. So what we found out is that in the center, we have highest concentration of titanium. Again, you see here the slides. This is titanium. And then you have this valuable green zone where you have the highest concentration of chromium. So with this, you can identify the source of color in your gems, but you can even go a step further. You do, like I told you, a chemical mapping of all the elements. This was at the very beginning when I was starting with working with things like this. So we were just monitoring 7 different elements. And then we tried different combinations like the sum of chromium and vanadium versus the ratio of manganese and titanium. And then we tried to identify if it is possible from a scientific basis to differentiate demantoid garnets from, for example, Russia, Namibia, or Italy. Newest ones are Madagascar. Sometimes it's easy. For example, if you have a horsetail, people always jump, oh, that's Russia, that's Russia. Well, in fact, it can be Russia, it can be Pakistan, it can be Italy, it can even be Canada. If you don't have horsetails, it can be either a clean demantoid or it can be Namibia or Madagascar. With the chemical analysis, we were able to separate, for example, Namibia versus Russia very easily. Italy is here in the middle, but we can see that we have some grouping together. And if you have an unknown sample and you measure chemistry that's up here, you can to 100% assign this as a Namibian garnet. If it's somewhere in the middle, it's more tricky. So in later papers, we have found out it is possible to assign many elements, do multidimensional analysis. Don't ask me about the details here. This is something that my brother is doing. So they put all this data into a computer, set up a couple of models, and then they separate them from in between all these different countries. And this gives you just an idea how accurate we can predict where the demantoid garnet comes from. For example, Namibia 93%, Pakistan 93%, Madagascar 93%, Russia 82%. Well, this is not that great. Iran, for example, about 74%. Italy is hard. Why? Because those overlap very often in how they were growing in terms of geology. And very often the samples that you get from collections are mislabeled. This is the biggest problem that we have in all this work. You can get the accurate chemistry for each and every sample, but if it's not from where it's reported to be, then you're just screwed. Yeah, so this was a little bit of what I would like or what I can share with you on chemical analysis of gemstones and why we use and how we use it, and why it's sometimes necessary that you go to a big lab and not to the next door gemologist in order to give you an accurate country of origin, for example. What we are trying to do is to go away from always expert-based opinions, go to scientific proof. Sometimes it's possible, sometimes you lack the data, and sometimes you have too much overlapping. So it's not the one solution that helps you in each and every problem, but in some problems, it can easily help you to differentiate if you had a good buy or if just somebody screwed you. Yeah, with this, I just like to thank you. And if there are any questions, please feel free to ask them.
I don't have any questions, but I do appreciate you giving me a lot of food for thought when it comes to the colorizing and also the using the chemical analysis to determine location. I think that that is not used frequently enough in the gemological world. And I just had something cross my path here a few minutes ago where coming back from Africa, we deal with Marilani mint garnet and how it fluoresces. Not really understanding the fluorescence, but one of our guests on that trip, he was comparing that to the uranium content glass, uranium glass. And it would be interesting, I think, to do your elemental analysis on Marilani mint and see what kind of return you get from the elemental analysis. But maybe a garnet is a too complex a material, because Lord knows it has just about every element in it sometimes. It's an amazing chemical soup. But to see what kind of results you could possibly get from that.
Well, I'm unfortunately not allowed to give you any results by now, but I can tell you as much as this. I got the HEA research grant last year for exactly looking into the garnets in the East African green chrysolar garnets and their fluorescence. And we have compared many, many mines from Kenya to Tanzania. Mostly, of course, we have Marilani material. Uh, and you will see the first results, the first presentation at the HEA conference in Tucson in February. So we're working on this for about close to a year right now with two professors, two master students, and a couple of other helping hands. So we do have quite some data already.
Excellent. I'll look forward to seeing it.
Well, sometimes fate turns in our favor, and I think we all owe a debt of gratitude to both Scott and to Clemens for having stepped into the fray today. But I think the other part of this is that we are aware now, more so than in the past, that the points of origin for gems are becoming more and more determinants in the valuation of the gems. And so for those people out in the gem world who have to do evaluations, the availability of the technology that's in the higher end labs now is making it possible for us to differentiate and be more accurate in terms of the points of origin for gems, diamonds, and color stones as well, and to differentiate obviously between synthetic and real. Those are things that are extremely important and valuable to not only ourselves but to our clients who depend on us for giving them accurate information and selling them stones that are at what they are supposed to be instead of what we think they are. So the science is now, the science of gemology is actually just blossoming in the last 10 years. And it's been very interesting to watch. And I think we saw a microcosm of that today between Scott and the presentation by Clemens. So thank you very much for attending. I will reiterate that Scott will be with us again at the end of September. And I'm very much looking forward to finding out about the geology and the gemology of what's going on in the African mines that that Scott and Vitor took a group to visit, and not that long ago, I think this month. So we're getting stuff fresh off the printing press, so to speak, and that doesn't happen very often in the gem world. So I'm looking very much forward to Scott's presentation. And in October, I think we're still trying to get a Zoom location that will help us because Clemens and others that he normally depends upon are going to be busy in the shows. So if anybody out there has a Zoom location that we can use for the October programming, I would very much appreciate you getting in touch with me and letting me know that we can avail ourselves of the services of that Zoom site. Okay, so thanks for attending. Thank you very much, Clemens, for your contributions, both as the support person as well as the presenter. And Scott, thank you again for stepping into the fray. And I hope we all learned something of value to us that we can use in our daily lives in the world of gems. And I'm going to sign off now and hope that you have a great month before we come on again in September.